Right, so we will now talk about topology. So what is topology? Topology studies the property of the remaining unchanged values when geometric objects such as point, line, and region were bended or stretched. And it describes the relative positions of features like connectivity, adjacency, containment, intersection, etc. Now, you can ensure that the digital geometric objects follow the specified topology relations by checking and processing the topology errors that might exist in simple datasets such as point, line, and region datasets. For example, let's say that we finished collecting vector data by vectorization, but we see that there are some topology errors that are not directly visible to us when we take a first look at it. And these can be two lines of a crossroad that are not connected. These can be overlapping points in a point dataset, and these can be overlapping vertices in a line dataset. Now, the topology rules in Supermap include the rules used for point dataset, line dataset, and region datasets, and as well as the rules used for several other kinds of datasets. Now, we're going to take a look at the help file, and we are going to see some of the rules and how they're constructed. So here we have the Supermap iDesktop 90 help file, and we have loaded up topology rules. Let's read it out for ourselves. So it says, validate topology is to return objects in point, line, region datasets that violate the specified topology rule. Validate topology is usually performed before data editing and topology analysis. In Supermap, there are 6 topology rules defined for point datasets, 14 for line, 10 for region datasets. Besides, there are 5 kinds of topology rules that can be used for different types of topologies. The topology rules used for point, line, and region datasets and the rules used for multiple kinds of datasets are introduced below. So we're going to take a look at the rules used for line dataset. Now, we have the ID here on the left. Then we have the description, and then we have an illustration. We're going to read 2 of 3 of these just to give you a general idea. So let's say we're going to read must not self-overlap. What does that mean? It means no self-overlap in the same line dataset, requires that line objects not overlap themselves. The self-overlap segments will be returned in the result dataset. Error dataset type, line dataset. Okay, so must not intersect within the line itself requires the line objects in the same line dataset not cross or overlap each other. Lines can share endpoints. The intersections will be returned in the result dataset as errors. Let's say we're going to read must not overlap with. So this requires that a line from one dataset not overlap with lines in another dataset. The self-overlap segments will be returned in the result dataset, error dataset type, line dataset. Right, so that was just a rough introduction to the topology rules, and we are going to move on to our next slide. Right, so our next point of discussion is why we need topology processing. While we collect our data and do some processing on that data, it is inevitable that we are going to get some errors. And what topology processing helps us with is that it can lighten manpower in data checking by automatically finding topology errors and providing editing tools that can fix those errors. Secondly, it can generate polygon datasets, and it can do that from a line dataset that has enclosed areas, such as to generate dataset of administrative regions from the line dataset of their boundaries. Finally, it can create a network dataset for network analysis. Now, a dataset contains not only arcs, but also nodes, such as traffic network, power transmission network, and pipeline network. So those are the three things that it can help us with. So now we're going to demonstrate how we can check the topology of a dataset. What we're going to do is that we are going to check the objects that don't conform to the specific topology rule. Let's go ahead and do just that. Right, so we have our dataset open right here in front of us, and these are supposed to be some roughly drawn districts that we have. And if we look at it right here from the naked eye, we see that they're perfect. Anyone would say that they're perfect. Like, they do look like regions. And on the first look, it doesn't look like they have any problem. But if we go deeper, we will see that there indeed are some issues with this. There are some mistakes that we talked about. So I'm just going to zoom in over here at this point. And there we have it. There are some imperfections in this data set. Now, we can go ahead and we can manually fix them. But imagine a really big data set. How are you going to manually eyeball all of these minor imperfections that are potentially all over the place? Now that's where topology comes in, and that's where a check of topology basically comes in. So we're going to go ahead and check the topology of this data set right here and see if we can identify all these three imperfections. So we're going to say data, the data ribbon, and under topology, we're going to say check topology. Now here, under the settings is where we select our topology rule. What do you want this check to do? So for this demonstration, we're going to use region inside, not overlapping region, right? We're going to leave the tolerance alone and the offset angle as well. And we're going to say, okay, so we have our topology check result polygon here, and we're going to drag this and drop it onto our current rendered map so that we can highlight those imperfections. And there we have it. So they have been highlighted, and we can even take a look at them as separate polygons if we turn off our original map layer. And you can see they have been identified, all three of them. And this is the main purpose of a topology check. Identification of errors so that you can correct them with the numerous tools that are available to us. Now, manual correction would work for these three, but as I mentioned earlier, if you have hundreds of small errors, manual correction would not work and you would need something different. And that is where the fixing of errors comes in. So let's talk about it. How do we fix these errors once they have been identified? Now, we talked about manually fixing them. We can use object editing, like things such as auto connect line, auto close line, auto split line, and auto split region, so that these can be automatically fixed. But these are manual ones. We can use object editing for these. There's a topology technique that we can use. We can use validate line topology to automatically fix all these errors. So let's see. We can validate and repair the topology errors of line datasets automatically with the selected topology rules. So we can set a no break object by entering the SQL filter expression, and the system will not break the line objects that meet that expression. So basically what these topology tools can do is that they can take a rule from the user and then it can fix the errors by following those rules. So let's see how that works.
Right, so here we have our sample data set open, and it shows a map in line form, and we're going to be demonstrating validating line topology using this data set. Now, if I select a line here, you can see that it is a long line that does not disconnect anywhere. So what validated line topology is going to do is that it is going to separate all these large lines, and what that is going to do is that is going to make it easy for us to be able to fix any errors that there might be. So let's go ahead and apply validate line topology here. So first of all, we're going to copy this data set because we want the original one for comparison purposes. So we're going to say copy data set, right? So we're going to say copy. And on this copied data set, we're going to apply validate line topology, and that is under the data ribbon, and under topology we're going to say validate line topology. And now these are the error handling options that we can use. There are intersect arcs, there are overshoots, pseudonodes, adjacent ends, duplicate lines, clean undershoots, and redundant vertices. So we're going to open up the help document and see some of these. Right, so we have taken this chapter out of the help document, and we are going to read some of these to get a better understanding of what validate topology does. So now, what is clean overshoots? If an endpoint of one arc is not connected to any other arc, this endpoint is called a dangle point. A line with a dangle point is called a dangle line. Overshoot is the line object whose dangle part is short. So if there's a dangling line in the scene, we can remove that automatically using validate topology. Extend undershoots. If an endpoint of one arc is not connected to any other arc, this endpoint is called a dangle point. So a line with a dangle point is called a dangle line. Undershoots in the line object whose dangle part is long. So overshoot is a short dangle point, and undershoot is a long dangle point. This is how all the other rules work, and it is recommended that you go through this chapter in the help file in order to develop a deeper understanding of what all of them do. So we're going to go back to our validate line topology operation. So here we are. We're going to select all of them, and we're going to go under advanced. Now for this particular problem, we don't need any no break object, so or no break position. So we're going to leave that alone, and as before, we do recommend reading more about this. So let's say we're going to keep the shoot at 10. We're going to leave fuzzy alone and overshoot 10 and undershoot 10 as well. And we're going to say okay and okay as well. Right. Right, so we're going to open this up and we're going to see if the lines have been made separate. So we can see that they have been divided into shorter segments because the shorter segments are easier to fix than one huge line. So this is what validate line topology does. It fixes most of the mistakes that you might have in your data set so that the remaining ones, which are short, you can fix manually. Right, so another thing that we can do using the topology tools is that we can use a line data set and we can convert it to a polygonal region. So let's go ahead and see how that is done. So we're going to open up our road_bf line dataset. There we have it. We're going to go under data, region by topology, under topology of course. And we're going to leave everything default. Just turn this one on and say okay. Say yes. And we have our build region_1 dataset. And there we have it. A region has been created. So finally for this tutorial we are going to talk about network by topology. So what's a network model? Now a dataset not only contains arcs but it also contains nodes, and topologic relationship exists between node to node, node to arc, and arc to arc. Now examples of networks are the traffic network, power transmission network, and pipeline network, etc. And a network dataset is used for network analysis. Now we are going to take our road dataset and we are going to create a road network like this. So let's go ahead and demonstrate that one. So we're going to open up our road dataset again. There we go. And we're going to go under the traffic analysis ribbon this time. And we're going to say network by topology, structure 2D network. Now here we have our dataset selected, which is road_bf, and we're going to say split lines at intersection. So we're going to have a point everywhere that lines intersect at. So let's go ahead and do that and say okay. We have our network here. We're going to open this by double clicking on it, and here we can see our topology network that we just created. So this is how you do a network analysis. So that's it for today's tutorial on data processing, data editing, and topology. So that's it for today's tutorial on data editing, data processing, and topology. Please turn towards the help document if you have any problems or contact us directly. Thank you.